Thank you. So, welcome to Show Me Your Data. My name is Nenad Kuzmanović. I am engineering team lead at 7Bridges. We are creating an awesome platform for storing, analyzing, and interpreting bioinformatic data. If you like to ask a question, go to this site. I will talk about alternative history of visualization, about cholera. I will give you a crash course about genomics in order to prepare you for human genome visualization. So let's start with the alternative history of visualization in Westeros. So I hope you all know and you all saw this TV show. It all started in 1951. The modern era of Westeros has just begun. Democracy has been discovered, and first elections since the first man invaded Westeros have been held. Votes from more than 4,000 places were collected and stored in a revolutionary storage system, a TSV file. So that's a TSV file. The data is there. You have the place, the kingdom, and the votes from my favorite families. I mean, there is not so much to see here. You can see that somewhere in the reach, Starks has 18 votes, Talis has 17. But I don't know. The data is there, and you can see it. That's nice. You can do some paginations, filtering, sorting, all things you can do with table, which is also nice. But you can't see the message data is trying to tell you. The message. Yes. Who won? I want to see the total number of votes per candidate. I want to see what their potential alliances. And you can see it like this. It's obviously Tyrells have won. Martells have 12%. Starks were good. But again, Tyrells won. And maybe if Starks and Talis go together, they are stronger, because in history, they used to be together. So I think there is a bit more information if you look like this. Yeah, but the dog is not impressed. I mean, you could do this like with the grouping by kingdom, making some sum. You'll have like 6 lines of result, and you could literally see the same. I think this is better, but not too many information. Okay, let's try something else. We saw that Tyrells has the biggest total support, but have they actually won? If you see the map, you could see that they didn't have maximum votes in all regions, only in 3 out of 10, which is not impressive. And their land is divided. They're surrounded by the Targaryens, Starks, and the Talis, which is, well, but which is not fantastic. Starks and Talis, if they go together, they are still not united. But if you look at this, maybe the Starks and Targaryens would be the perfect alliance, because they will hold like the northeast of the land. Okay, still not impressed? Okay, I want an interactive map with the vote distribution per kingdom. I want to know how they vote for every region. And I know if you notice, it's kind of suspicious that Starks didn't have a majority of votes in the north. So, yeah, much better now. I see the Starks, yeah, won the way alliance, there's 14%. I can see the north, only 19 for the Starks. Targaryens won the north, which is kind of strange. But in this visualization, you can see Tyrells should maybe in the future think about Westeros lands and the Reach, because they're pretty good there. And maybe on next elections, they should work more there and have like united land. Also, if you look the Starks and the Targaryens, if they go together, because Starks has the big support in the riverlands, they could unite like whole bigger part of the country. But still, it's kind of strange why the Targaryen have won the north. So let's talk about Lord Varis. He is a master of whispers in King's Small Council. We know that he can move very fast across the map. And he was very active during the voting, so we kind of recorded his location periodically. And, well, the format of data is a latitude and longitude array, something like this. And I want to include this data on the map. So it's basically TSV plus locations, just a bunch of numbers. Okay, this is his positions. He was 4th time in the north, and the Targaryens won the north. He was never in the gift. Yeah, they had 3%. Then he was, come on. He was in only once in Riverlands, well, 8%, not bad. He was 3 times in the Crownslands, and they won. So I don't know if you see the pattern maybe here. He was 3 times in the Westerlands, 19%, not bad. He was never in the Reach, only 1%, and he was never in the Dorn, less than 1%. 2 times in Stormlands, 18%. So the point is you have like 2 different data sets. You have TSV file and some locations, a lot of numbers. You cannot see what's going on, what's the message of the data. But if you somehow do the visualization and put these 2 data sets on the same place, you could understand that Lord Varis had to do something just to make Targaryens and Starks to go together. So finally, TSV or visualization, yes. I mean, the data is in TSV. TSV is a data, location is a data. But with visualization, you can actually understand the data which is inside. Okay. Back to the real life. It's 19th century. There was and cholera, yeah. There was a big problem with cholera in 19th century, but it brought us some cool visualizations. For example, this is New York. Well, the total number of weekly deaths and deaths by cholera. You could see on this visualization that, yeah, we have a problem with cholera, but there is no solution. A little more descriptive was the heat map of Paris. So they actually had the regions of Paris marked where is the big death rate of cholera. Bit more information, but still you couldn't find the cause of cholera just by looking at this map. And then there was one doctor who actually took the map of London and he marked every death on this map. And then he said, here we have a problem with cholera, and he wanted to try to find the cause. And he understood that he need another set of data. So he added the location of the water pumps. And he understood that this water pump was the problem. And the doctor's name was... Yes, his name was Jon Snow. He is the father of the modern epidemiology. Yeah, visualization. The point of visualization is not about adding sparkles and shiny colors to your application so somebody could say, wow, it's so nice. No, it's about sending a message. It's about communicating a message hidden somewhere in the data. Or how the old Westeros proverbs say, a picture is worth at least 1,000 times 4 rows of data. Okay, show me your genome. What is genome? I'll give you a crash course about genomics, seen like from perspective of software engineer. So let's start with DNA. DNA is a string containing A, T, C, and G letters, which are actually called bases. It could be various length and combination. It isn't actually just a set of random letters with no order, but it's a string. What's a gene? It's a short section of DNA. It actually presents information with instruction for how to make a certain aspect of you. It's a blueprint for everything, but for a software engineer, it's just a string. Chromosome, a package of genes and other bits of DNA. Again, it's a string. And genome, it's organism's complete set of DNA, and yes, it's a string. So it looks like this. You have chromosome, you have you have gene, you have bases, actually base pairs, but if you know only one side of this double strain, you will know the other one because they are always complementary. They are always connected to the complementary base. Fun fact number one, backend and front-end developers are 99.9 identical in their genomic makeup. Everybody here is 99.9% identical, right? Yeah, one more example. So genome is a book. It's your unique book, your biography. It's instructional manual of you. It contains 45 chapters or 46 chapters or 46 chromosomes, 23 from your mom, 23 from your dad. Each chapter contains paragraphs. These paragraphs, or some of them, are genes. And everything's written with 4 letters. So basically, it's a long string. For eye color, open your book, go to page 63324, chapter 2, and check first 150 letters of a second paragraph. If you have your books now, everybody would see his eye color. Yeah, this is how it would look like. Fun fact number 2. Humans share 50% of their genes with the banana. And really important thing, it's the difference between DNA and RNA. That's it. Single chain, double chain. I mean, you don't need to know this. I just want to put it on the presentation. Okay. Well, human genome has 3 billion base pairs. If we code it with 2 bits, because there are 4 of them, you'll get around 750 megabytes, which is the size of one awesome CD. I hope you guys know what the CD is. Imagine that it's your awesome, like a music disc. It's your personal music album. How awesome is that? Well, not awesome, not as awesome like this one, or this one, or this one. But still, it's yours, it's unique, and that's why it's awesome. So when I say show me your data, I don't mean I don't think about some data you have in database. It's like your personal data. It's your genome. But how? So we cannot just scam people and take this 750 megabytes. Maybe in 10 years, according to this movie. But currently, we don't have the technology. We need to do something called genome sequencing. So what's genome sequencing? Well, it's a process of basically digitalizing your genome. Like I want to have it in a file. You have some steps. First is library preparation. It's done by scientists. They put some, they take input sample. They isolate the DNA with some chemical reaction. Next step, they use the fragmentation. It's literally ultrasound wave that is breaking that chain in small chunks. It would be like you take 10 copies of your book and you shred it. So you have smaller chunks. 200 to 500 letters or base. And some of them would overlap because you have 10 copies of your book. So sequencing. Once you have your shreds, you basically put it in one machine called sequencer, and the output would be a FASTQ file. That file containing, it's literally, it takes one shred and just write it down. I'll call this one ID1 and it's ATTCCGC. And the machine do it for all shreds. So DNA fragments, DNA sequencer, these sequences or reads now stored in a file, and you'll have the FASTQ file containing random sequences from multiple copies of the same DNA or of your book. So how it's actually working, the sequencer. So somehow these double strains are separated. Remember Danny's hair, so it's separated, and now, well, they want to be connected. And then the scientists prepared the bases with attached fluorescent on it. So these bases are now connected to the separated strands. They connect to the complementary bases, and they literally take a picture of this and translate color array to a string array. Actually string. So that's it. That's how the sequencer work, and the output is FASTQ file around 100 to 300 gigabytes. Okay, now you need to align this somehow. I mean, you have just random shreds of your book, and you need to align every piece to the right position, right? So this is something that's done with the software. The software literally take one sentence and search through the something called the reference genome. So it have to find the position of one shred, and it's compare it to the thing called reference genome. It's a genome assembled by scientists as a representative example of a species set of genes. So imagine you take one shred, it says the eye color, then you open the reference genome book and you start searching for a sentence that starts with the eye color, and then you put it there. It could be exact match. It could maybe belong to the more than one place, or you could have like not exact match, but very good. Imagine sentence with only one different letter comparing to the reference genome, and you would say, yeah, okay, I'll put this here, and I say this is a mutation. So what's a mutation now? Mutation is literally change of the letter. Let's say it should be C there, and now we have the G, for example. Yeah, input is reference genome and FASTQ file, and the output is a BAM file around 10 to 100 gigabytes or more. BAM file is basically this reads from FASTQ file but aligned. So let's talk about mutations. Unfortunately, they are causing Daltonism, cancer, or autoimmune disease. But they also can cause super strength, immunity to pain, resistance to fat, super speed, or shock-proof skin, which could withstand voltage high as 20,000 volts. I mean, regularly will be fried on 50 volts, and we have a local guy called Slaviša Pajkić, the battery man, or Biba Struja. He has this mutation. So why are we sequencing genomes? Well, for example, with the sequenced genome, you could do a prenatal test. Prenatal test is a test for detecting problems with the pregnancy as early as possible. And I like this example because my wife is pregnant, and oh, thank you. And after we got the results, I actually understood that they did the sequencing of genome and ran some software on the FASTQ files, which is awesome because at Cyberbridges we kind of do something similar. The baby is fine, no issues, and this is us. Okay, prenatal test. First you have to make a baby, then take a blood sample of mother after 10th week. You sequence DNA, have a FASTQ file, you know how to do this. You run a aligner tool, that's software for aligning the shreds of your book. You run the prenatal test tool, it's basically a software. Imagine like command line software, which will have input files, the BAM files, and it will just output the text file with the results. And that's it. But if you run this on your desktop machine, think about 300 gigabytes file and heavy computation. We have some tools on our platform that could last for days on 35 CPU and 64 gigabytes. So imagine you start a task, that software, and now what? Now you just leave your machine for 3 days. There is a better solution. on Assembly platform. So make a baby, sequence DNA. You upload the FASTQ files to Assembly platform. Now you create a pipeline with the liner tool, and then so input files going to a liner tool, output files will now go to prenatal test tool, and you click. So at that moment, in the background, the new instance will be allocated. All the tools will be downloaded to that instance. Okay, they are Dockerized, and all files will be downloaded. All computation will be done, and you will just get your files on your project. And then you could run a Genome Browser visualization and check the reads and mutations manually. This is an example of pipeline on our platform. So you have some nodes are input files, some nodes are these tools, and after all this, you finish with the output files. Finally, Genome Browser, it's a front-end visualization. It looks like this. Bottom track is reference genome. We call it faster track. I hope you recognize the reads. So one line is basically shreds from one book aligned. So there is a lot of books for this one. Blue line chart is just the density of the reads. And yeah, basically there is a lot of them here. The colors you see are actually mutations, but if you look vertically, if there is only one mutation, it's probably just an error on sequencer. I mean, it could make errors, so you can zoom in, zoom out. You can check the mutation, but again, this one is not mutation because it's only on one read. You can, yeah, okay, there is no mutation. You can show all the letters or bases. You can browse through the genome literally with the drag and drop or using the arrows. You can go to exact position. You can choose the, you can go to exact position. You can choose the chromosome, or you could, play around with your genome. Genome Browser is actually a bit bigger. We have like 5 tracks, the chromosome, the BAM you already know, VCF track, gene track. VCF is all known mutations. Gene track is showing the genes, and fast track is reference genome. There is example with someone who actually have the mutation on one position. I have no idea what this means. It could be nothing, could be super speed, could be some disease. I don't know. Okay, we'll talk now about BHLHE41122627 5297. This is my favorite mutation, and we'll try to find it in the Genome Browser. In Genome Browser, you can you can just write down the gene, and it will automatically take you to the that chromosome, that position. You can check there are some mutations here, but I want this exact position, and I want to check if G mutated to C. Yeah, you just write it, just a number, and there is no mutation here. So you can actually check by toggling bases. It's G. This mutation or variant is associated with short sleep and resistance to sleep deprivation in humans. That basically means if you have C instead of G here, you could like sleep 3 hours and feel very well in the morning. You could go out partying, come or coding all night, and come back at 5, sleep 3 hours, and go fresh to work. Okay, Genome Browser. What was the problem with Genome Browser? Well, you have to visualize large file contents, and you can't just load 100 gigabytes in a browser. So also the content is in file; it's not in database. So we needed to create a backend streaming service which will stream files from Amazon. Then you have to somehow send only smaller chunks to the front end because of the limitation of the internet and also limitation of the browser. I mean, When you develop on your machine with i7 processor with 16 gigabytes of RAM, it could work, but you have to think that somebody is using like Internet Explorer 10 on Windows XP and slower machines. Then one of the problems was you need to synchronize all these tracks and the top bar, the position, any change of position, any change of the chromosome or reference genome, everything should be very well synchronized. You need to get the right chunk of a file. Well, for example, when you drag and drop the sum of the tracks, you now have to translate the pixels to position. You send position to the backend. Backend now have to stream exactly the selected chunk of the file, which is binary file. Then the backend need to pack it in the nice JSON to send it back to the front end, and you also have to render it. So there's a lot of stuff going on which have to be perfectly synchronized. Yeah, it should work performance, and it should have some interactivity. Why Canvas? Well, we had to use Canvas because there was a lot of objects. I'll mention this later. But it's a bit harder to add interactivity to the canvas. Yeah, memory leaks. When you have a large application, you have to check for memory leaks because in 5 minutes of using application, you could literally crash your browser. It's written in TypeScript because it's awesome, and it's a very large front-end application. It's more than 300 kilobytes compared to jQuery, which is 250. Yeah, Webpack is used for bundling. It's huge application with huge directory and file structure. We use Redux for state management because we need state because you have top bar, a lot of tracks, a lot of data. RxJS observables are used for communication and change between tracks. Miroslav had a great talk about RxJS. I hope you heard him. Yeah, of course, you have to repaint all tracks on each position change. Yeah, I didn't say that it's not only a BAM file. So each track has its own file or database. So each moving should actually trigger some request for backend to backend, and each track will be separately rendered. Yeah, okay, we have a backend for Java service for streaming and Python service for some comments. I didn't show that, it's not that important. Yeah, tracks are drawn on canvas. Why? Well, big number of elements. SVG wouldn't be performant. Voting in Westeros. This is SVG. I used D3.js. It's really awesome library for visualization. Try it. TypeScript and Webpack because they're awesome, of course. And I'm not going to teach you D3.js. I'm just going to show you this is the code you need for generating the map. It's kind of 14 lines of code or less. You need something called GeoJSON, which is basically a JSON with polygons which should be drawn on the map. Try this at home. You can literally try this at home. There is a company called Dante Labs. They'll send you like kits, which is basically a tube. You spit in a tube, you send that to them, and they give you your digitalized genome. They give you a FASTQ file. You can then upload it to 7bridges platform, go to Genome Browser, and watch your genome. If you would like that, I wouldn't. SVG and Canvas. SVG is part of DOM, so it's easy to manipulate, select, remove. It's easy to add events. Canvas is one HTML element, and once you draw something, you cannot use that object anymore. It's there, but no events. You cannot remove it. So, you need for Canvas you need to keep the records in your script. Basically the array of all elements you draw on Canvas. SVG is great, but not performant for big number of elements. Up to 30,000 is okay, or 10,000 with animations. For example, in Genome Browser, we have like 50,000 elements only for the BAM track, and we have 5 tracks. So the canvas was obvious solution. Good performance for canvas, but a bit harder to manipulate elements and to develop. There is also WebGL, best performance, hardest development. And sometimes you actually have to render images on the background, on the backend, because imagine you have a scatter plot with 10 million of dots. I mean, it's why would you send so many data to the front end when you can just render it on the backend and send image? And that's it. Thank you. Just one more thing. I mean, you're the best audience I ever had, because this is my first conference talk.
Thank you. We had a bunch of questions. Unfortunately, most of them were spam, so I would like to kindly ask you to not spam the channel, only ask the questions that are relevant to the talk and that are relevant for the entire audience. So, first question is a bit more technical on the other side. Can the mutations easily be mapped to super strength or flaw such as Daltonism?
I'm not sure I understand the question, actually.
So I guess DNA mutations, can they be easily mapped to what the consequence will be of this mutation?
Well, yeah, but some, I mean, this is more question for bioengineers, but bioinformaticians, but yeah, there are some mutations that are known what they do. So yes, we know which mutations are causing some of the disease. Not all of them, but yeah.
Okay, and again, bioengineering.
Okay.
Are these researches helping you find the cure, or whoever is using those data find a cure for diseases?
Well, the examples I showed you were literally the basic examples. They actually, when they do the researches, they have a lot of files. They try to, for example, they have samples from a lot of people died from specific kind of cancer, and they try to find all mutations that they had, for example. And that's the way they use our platform for the research. But again, I don't know the details of that. Okay,
now the first technical question for you. What is the direct advantage of using Genome Browser?
What is the advantage?
Yes, versus not using it.
Well, I mean,
apart from the
I mean, you can see your genome. You can. I mean, it's Genome Browser. Why not?
Okay. Are there some other similar tools on the market?
Yeah, there are some desktop tools, and I think that there. I mean, it's IGV. It's a desktop tool, which is cool. But again, from technical point of view, it's easier to have it on your desktop because your files are there. And you don't have this problem with streaming files to the front end, with requests, with rendering the application in the browser. But yeah, there are other tools.
Okay, so related to this, how are your local dev environments set up? Do you depend on cloud during development?
Yes. I mean, you start basically the front-end application. I mean, the Genome Browser is actually, we made it as a library, which is later it's packed and it's included in our front-end framework. But when you develop it locally, you actually start that application, and you need to have like kind of providers which will fetch data from our development servers.
Okay, one side question. How do you mock the data when you're testing this? I mean, usually when you have to build some relatively simple code and you have to mock some data, it's difficult. I cannot imagine mocking the full DNA.
Well, I mean, is it like, okay, if you write tests, you don't need to have the whole DNA. I mean, you just need basically to have one response if you want to write tests. But again, while we develop, we use this public data, which is on the development servers.
Okay, and next question, sorry. Did you start with GIFs and shape the talk around them, or you actually found GIFs perfectly fitting your talk?
First one.
Okay. And then I guess this was kind of a mixture of your private life in a way and the talk. So the question is this an IT lecture or are you actually talking about your life?
About my life, of course.
Okay, thank you very much. One more applause.